Welcome. I'm Pat Reed, Cornell University. Um, and we're going to just give it a couple minutes while folks log in. Uh, just getting a confirmation you all can see my slides and hear me okay?
Yes.
Excellent. For those of you joining, we will be recording today's webinar and posting it to YouTube. All right, we've given it a minute or so. I don't want to steal more time from our speakers. Welcome to the 2026 webinar series for Multi-Sector Dynamics Community of Practice. Very happy to share the quantum computing futures through a multi-sector lens webinar. If you haven't participated with our webinar series, just a few rules. Please be considerate, respectful, and collaborative. Keep muted unless the facilitator calls on you to speak. Maintain a supportive and positive environment and respect any questions or input from other participants. This is part of the Multi-Sector Dynamics Community of Practice. This is an initiative that goes back to 2020, and it's an effort to accelerate development of needed foundational capabilities in human Earth system science through open science and a growing transdisciplinary workforce. If you're interested in thinking about visiting AGU, you can use this QR code and it'll take you to a website with the very large number of multi-sector dynamics sessions. I'm not going to go through and read every one of these titles to you, but if you go to that website, you can find every single session. And for the last 5 years, we've had a very large and I would say engaging thematic set of sessions and posters. And so highly encourage you to participate. And if you're interested and haven't signed up, you can sign up at multisectordynamics.org. Join us. You can get our newsletters. You can check in on our working groups. We're also on LinkedIn, and you can follow the various activities. And as I said, we have webinar series, and our next really big engagement is going to be the fall 2026 AGU. And with that, I'm happy to pass to Gokul.
Thanks, Pat, and welcome everyone to this webinar. I'm Gokul Iyer. I'm a staff scientist at the Pacific Northwest National Laboratory, and I'll be moderating today's webinar. The topic of today's webinar is quantum computing futures through a multi-sector lens. This webinar will feature two presentations that will outline and give foundational basics for what quantum computing is, its complex multisectoral interactions and implications for energy, water, and other sectors like the material and supply chains and so forth. The first presentation for today's webinar will be by Olivier Ezratty, who will introduce the quantum computing, give some basics about quantum computing, its expected applications, its added value, hardware requirements, and so forth. Olivier will also talk about the energy implications of quantum computing systems. After Olivier's presentation, we'll have a talk by David McCollum, who will highlight the multisectoral challenges and opportunities and trade-offs and across various systems and how they interact with quantum computing and data centers and so forth. In particular, David's talk will focus on the long-term future and resource impact of these novel systems and potential choke points. So with that, I guess I'll turn the floor to Olivier. Before that, I'll just give a quick and very short introduction about our speaker, Olivier in particular. So Olivier is a quantum engineer. He's mostly known for understanding quantum technologies, which is a comprehensive open source book on quantum technologies. He is a teacher and lecturer on quantum and classical technologies at a variety of organizations and universities. And we're really delighted to welcome Olivier to this forum. So with that, the floor is yours, Olivier.
Yeah, I think you can see my slides. Yeah, and on top of that, I'm one of the co-founders of the Quantum Energy Initiative, which I'm going to talk about in the course of my presentation. So the goal you gave me, guys, was to explain what is quantum computing. So I will try to be very concise in explaining that. So basically, it starts with quantum physics. And if you are not knowledgeable about quantum physics, it's good to know a little bit about that. So quantum physics is based on a set of principles and postulates. Uh, the main one is quantization. So some quantum objects like atoms, electrons, and photons have specific properties which can be discretized. And it's particularly the case for energy levels in atoms when you excite an atom of hydrogen, for example. And there are some weird properties like the spin, which can be up or down in a given direction, and others like angular momentum for photons and electrons. So these are discretized properties. The second property that we are using in quantum technologies overall is the wave-particle duality, when all these objects and their properties can behave as wave and particle simultaneously. So usually they behave as wave when you interconnect them, when you kind of create interference between them, like in the famous Young sleep experiment, which has been done for photons, also for electrons. But sometimes it can behave as particles, like when a photon hits an atom, it can displace the atom. The two other properties which are very important are superposition and entanglement, which are both a consequence of the linear properties of the Schrödinger's equation, which drives the operations of all these objects and their properties. And entanglement is probably the weirdest, which is about connecting objects and making them interdependent, at least at the level of their properties. And this is a very significant property that we use in quantum computing. So I'm going to be very short on that, but I will make the connection between those four kind of simple elements and the way we use them in quantum computing. So quantization is about having different properties and discretization, and we use them in qubits. And what's a qubit? It's a two-level quantum object. So it's a quantum object where you manage one property which has two different values, possible values. And usually in a quantum window, we use a certain number of qubits, let's say n qubits. The wave-particle duality is used with generating interferences between those properties and those objects. And it's one of the key features that's being used in a quantum algorithm. The third one is superposition. It's what drives the kind of the power in memory management, because when you use n qubit in a system, the internal, let's say, data space has a size that's exponential with the number of qubits. So you have 2 power n complex numbers. But in the end, when you measure the results, you get the classical bits, and the measurement is probabilistic. So that's the weirdness of computing here. And the last one is entanglement, and it's a way to connect qubits together. And it's one of the contributors to the speed up that you obtain in quantum algorithms. It's not the only one, there are many others, but this is the one. So the big question that anybody should ask before even explaining how quantum computing works is, what's the potential benefit? The initial benefit is about solving problems that are inaccessible to classical computers. So it was the dream of Richard Feynman back in '81, and he thought about the relevance of using a quantum system to simulate other quantum systems. So it made sense from the semantic standpoint. And so the kinds of problems which are in that situation, I'm going to explain them later. It's mostly about chemical simulations or optimization problems. The second one, which is also very relevant, particularly in scientific computing, is to improve the results, the quality of the results you want to obtain. So let's say, for example, I'm a chemist, and I want to obtain a ground state estimate or free energy estimation for some molecular compound. I'm interested in the accuracy of that chemical simulation even more than computing time. So it's another thing. It's the same when you kind of try to do optimization using heuristics. You want to have a better result, even though it may not be the best one. The third one is to reduce the required training data for machine learning tasks. It's one potential benefit. It's not proven yet that it works, but it could happen in some situations. But all of that is can happen in a given context where this is not replacing classical computing. So all the HPCs you have at the DOE, for example, they will still be used. Then what's very important, and we'll explain that a bit later, is that all quantum algorithms, they need classical computing. So there's no quantum algorithm or quantum computing without some classical computing around it. So it's the reason why many observers say that a quantum computer is kind of an accelerator to classical computing, like a QPU, which serves a kind of similar function as a GPU in HPCs right now. And so in the end, you will have systems, and that's probably the stuff that David will discuss about. We have a combination of HPCs and quantum systems in most places, particularly on scientific computing. So now let's talk about the problems that we want to solve. There are 5 kinds of problems. The first one, which is motivating a lot of people in research and the academic, and also in some industries, is to simulate quantum physics. So simulate quantum matter, simulate materials, semiconductors, simulate condensed matter, also simulate any chemical compound. It can be gaseous, it can be liquid, it can be organic, non-organic, it can be related to energy production, for example, or consumption. So everything that has molecules and electrons and orbitals could potentially be better simulated in a quantum computer. The second is combinatorial optimizations. That's more for industries and banks, for example, in financial services. Then you have machine learning and deep learning, which is questionable right now. We don't know yet if we're going to have some benefit, but still it's a very interesting research domain. The fourth one is solving PDEs, so partial differential equations, which can be useful in fluid and CFD, so fluid mechanics. It can be useful in engineering. It can be also useful in financial services. A lot of Monte Carlo simulations rely on that for optimizing portfolios, for example. The last one is I would say, the less useful, but everybody's talking about, is breaking the web. It's breaking the internet. So breaking asymmetric or symmetric cryptography keys. So we call it cryptanalysis. So it's based on surprisingly, it's based on the only quantum algorithm which has a proven exponential speedup. That's the only one, the Shor algorithm, which there are 2 Shor algorithms, by the way, one for factoring integer and the other one called discrete log. And those 2 algorithms from Peter Shor, which were invented in 1994, could potentially break the web. So it's kind of red because it's negative, it's destroying. Of course, there are some countermeasures around that, particularly post-quantum cryptography. So now, who is concerned? So there are, I would say, 3 kinds of organizations which could be interested by using quantum computer, either an existing one or a future one. One is the organization doing fundamental research. So the DOE is part of that. I mean, when you simulate high energy particle physics, nuclear fusion, even the nukes, when you simulate stuff in astrophysics, when you simulate condensed matter, it's really fundamental research, which is not necessarily connected to the industry. The second kinds of players are the companies who want to create new products, mostly hardware products, like batteries, new processes, new chemical processes, like to produce fertilizers more efficiently, or drugs if you're a pharmaceutical company. All these companies, they need digital twins tools to develop their products. And so they need to do some fundamental and applied research, but to produce something. And there's an economical relevance to do that. The last one is more remote. It's business ops on a day-to-day basis. So these are the companies like transportation companies, logistics companies, financial services companies, energy utilities, who want to optimize their process mostly on a day-to-day basis. So if you take, for example, an energy utility, which is probably a topic that's relevant for you guys, these are the companies who want to optimize the energy distribution because you have a lot of renewables, intermittent energy sources, and variable demand, particularly when it's heating or cold. And so you need to adjust the offer against the demand, and it needs to be nearly real time. And that's where optimization come into play. Even telecoms have needs, and they need to optimize the bandwidth of their systems, the base station location. They need solve a lot of optimization problems, which they do classically right now. But if there was some quantum algorithm which would enable the generation of better solution, it would have some economical value. But what I've got to say here is there's a paradox. The paradox is the following. If you go on the right, the market is larger. because the market of business ops is a large market because it's the cloud market, it's business ops for many, many different organizations in many different industries. The middle market in green is mid-size, and the market on the left is non-commercial. It's purely academic, funded by governments. It's probably smaller. And the paradox is the following. The more you're on the right, the larger the market is, but the more you're on the right, the fewer proven quantum advantage you have right now. So we need to develop new algorithms to really find a way to solve the problems on the right. When on the middle and on the left, there's probably a better opportunity to solve problems efficiently with quantum computers. So all the stuff related to energetics and the interest that you have at MSD is connected to the red zones. So it's a lot of zones. I mean, developing new products related to energy consumption or production, optimizing the energy consumption in multiple domains like transportation and logistics and energy utilities. So it makes a lot of domains which are relevant to the topics which are interesting for you. And so, well, as a result, there are a lot of people who try to look at this question. And I participated recently to the creation of this kind of white paper, which has two components. It's coming from some lobbying group in the EU. And it contains one part which is dedicated to the usage of quantum computing to solve problems in the energy domain. And it contains a smaller part which is related to the energy efficiency of quantum computing, which is the topic of my talk, or the rest of my talk, based on what I do at the QEI. And so let's do a little bit more basics. So quantum algorithms, so there's a lot of, semantics to share there. So a quantum algorithm is a series of operations that you apply to a series of qubits. So you have here n qubits. They don't necessarily are aligned like this, like lines. Maybe they are in 2D or in 3D, in space. It depends of the way you implement the qubits. But from the logical standpoint, you have qubits who have a life, and the life is over time. It's from left to right. And you apply operations to the qubit, which shows up in the 2-qubit gate, single qubit gate, or 3-qubit gate. These are operations that either modify one qubit independently of the other, or operations that modify the connection between the qubits. And so a quantum algorithm, what's its role? Its role is to solve a mathematical problem and to generate such a circuit and to execute it on a quantum computer. The quantum circuit is a series of operations on a quantum memory, on individual qubits and connecting the qubits together. And basically, what is implemented in such a circuit is very simple to some extent. It's just matrix computing. It's linear operations on a memory of 2 power n complex numbers. It's like every gate is like multiplying a matrix with a vector. The vector is the gate, and the matrix is the representation of what's here. And so the mechanism that's used by a quantum algorithm is very different from a classical algorithm. It's basically about using constructive and destructive interferences in the state vector, which represents the data in the system, to yield a value of interest. And in the end, you still need classical computing because it's used to prepare the circuit, to create the circuit. Usually there's some software that creates the circuit, encodes the data, and extracts some useful result from multiple circuit runs and measurements. Because if you use the circuit only once, you get a random result. So you need to execute the circuit multiple times. Let's say, for example, you want to run some chemical simulation. You will run it at least a couple thousand times, which depends on the number of orbitals in your system and the accuracy you want to reach. But you need to run a lot of times your system. And then you do some kind of weighted average of the result to get some useful result. One important aspect is every time you do something, or even you don't do anything on the circuit, you get some noise. You get some errors. It's very different from classical computing. When you use your GPU and CPU, there's no error. Or at least I think it's 1 error out of 10 power 18 operations. It's very minimal, and it's corrected. In the case of computing, in a quantum computer, every time you do an error. And the errors you will see later are significant. Right now, you have about 1 error out of 100 to 1,000 operations. It's a lot. So let's say you want to run 1,000 operations, and you have 1 error every 1,000 operations. In the end, you will have a random noise, random result. So the size of your circuit, number of qubits, and the depth, meaning the number of columns you have in the circuit, it conditions the fidelities of your operations. And the formula is very simple. The error that you accepted, so epsilon ops, must be smaller than 1 divided by the size of the rectangle, n times d. It's very simple. And so E ops is constrained by all the errors that you have: initialization, single and 2 qubit gate errors, idle state. When you don't do anything, there's errors because there's a drift in the qubit value. And even the readout generates some errors. So you need to control those errors. So now, what are the needs of the people who develop applications? The people who develop applications, they need to run circuits which are fairly large. If you look at this consolidation that was done by NERSC, which is part of DOE in the US, they look at 3 domains: high energy physics, chemistry simulations, and material simulation. And what they found out is in most of the cases, you need at least 1 million operations. When existing systems support between 1,000 and 5,000 maximum, and you need at least 100 logical qubit, and the bulk of the key high-value solutions need at least 1,000 corrected qubits. So we call it logical qubits, which I will describe later. So now let's look at the physics. The qubits that are being exploited in a quantum computer, they are very different types. There are 4 key categories. One is atoms and ions, single atoms and ions that you control with the energy level. Superconducting qubits, which are used by IBM and Google and IQM and Rigetti and others. These are kind of so-called artificial atoms. These are harmonic oscillators running in a loop at a very low temperature. Then you have spins of electrons that you can control, and then photons. And all of them have a physical aspect. And with the exception of cold atoms, all of them rely on some semiconductor. So when you control an ion, you use a semiconductor that uses voltage that controls the position of the ions, and sometimes it sends microwave or electrical RF signals on them on top of lasers. Superconducting qubits, it's 2D circuits driven by microwaves. Electron spin is driven by voltage, I would say flux current, DC current, and microwave pulses. And photons, they use photons. So they are the microwave guides, and it's still nanophotonics on 2D circuits. So all of them are always using a form of electromagnetic wave, either in the microwave domain or in the optical photon domain. So that's the basic of the functioning of those systems. You have many players in that space. I think there are now about 90 companies in the world who try to develop those systems. Out of the 90 companies, only about 25 have an existing system. We call it a noisy system, a NISQ system. And some are in the cloud. So, for example, the D-Wave, the Rigetti, the Continuum, the IonQ machines are available at Microsoft and Amazon Web Services. IBM has its own cloud, and it offers its own machines on the cloud. And there are many different categories. So 8 categories and even 20 subcategories, and many, many different players. So I could comment on all of them. They are more or less serious. Some of them raised more than 3 billion in cash, like IonQ. And IBM has decided to invest 10 billion recently over 5 years. And some startups, they just raised about, let's say, 20, 30 million. So there's a big gap between the small chips and the large companies there. So there are a lot of challenges to address in that space. One is the qubit quality. The second is error correction. The third is electronics, cabling, and cryogeny, which has a lot of relationship with the energy consumption. And then you have interconnection, because at some point you will need to interconnect multiple quantum computers because they can't scale that much. And you need sometimes quantum memory to run some algorithms. So it's a new, I would say, a new kid in town that has to be developed. So now I explain you that you have noise and that the existing systems, they can't run more than a couple of thousand gates in a circuit. So if you want to run more, you need to develop a technology that we call FTQC. So it means fault-tolerant quantum computing. And basically, FTQC is based on 2 components. The first component is to create logical qubits, which are collections of physical qubits, and which exhibit a longer lifetime and a better fidelity over time. But you don't do any operation on them. It's just something that is stable over time. And it has to be stable over the duration of your circuit execution, which can be long. Sometimes it's in months or at least weeks. On top of that, fault tolerance is adding the support of logical operations on this logical memory, and it has to support a broad set of quantum gates, and there's a lot of complexity there. It must also avoid the propagation of errors as you do implement your logical gate, and you need also to have a fault-tolerant readout. And all that is dependent on a lot of figures of merit, the connectivity between the physical qubit, the physical fidelities of the operations, the software that you use to do error correction, and in the case of photons, the number of photons you lose or the number of atoms you lose in the system. And there's many, many different engineering aspects in the way you implement that, which condition the cost of the system and its energetic cost. Recently, there were resource estimates which were striking because it was about breaking the web with RSA 2048, so the keys that protect the web today. And there were a lot of papers being published which say, we're going to have the capability to break the web with only 10,000 atoms. So it shows up on the left with the Oratomic paper, and Oratomic is a company which just raised earlier this week $300 million in California. And but actually, when you look at the details, most of the case for the atoms on the top, they are too slow because the time it takes to solve the problem in that case, it's a couple of months or years or even decades. So it's way too slow. And in the case on the top, it's really too slow. I mean, it's more than 10 years. I mean, it's more than the MTBF of a laser in the system. On the right, it's too many qubits. So we know that to reach scales with millions or tens of millions of physical qubits is going to be very hard, at least in the next decade. So the sweet spot is in the middle. So the sweet spot is about having systems between a couple tens of thousands of physical qubits up, let's say, to 1 million. Even 1 million is a very stretch. And with a quantum computing time, whether for doing this or to solve some chemical simulation problems, it should be less than a month, I mean, to be serious, which is the case also for HPC computation. When you look at the state of the art today of physical qubits, this chart is something I've been updating for at least 3 years now, with the different kinds of qubits in the colors that you have. So many blue, because that's where you have a lot of IBM systems and other systems in superconducting qubits. What you see here is that the fidelities are kind of in between 1 error out of 100 to 1 error out of 1,000. So between 1% error for 2 qubit gates and 0.1%. And the maximum that I know is about 1,600 physical qubit, even though I'm not sure it's fully well integrated. And so if you look at the progress in the last 2 years, these are the dots that you have in the rectangles. So I think it's atom computing on the top. In the middle, it's superconducting qubits. And the small one with 2 physical qubits with, like we say, 4 nines of physical fidelities. It's 2 qubits from Oxford Enix, which now belongs to IonQ. And we need to go way up. We need to go at least at 10,000 to 100,000. And we need to go up around the 0.1% error. So it's a huge challenge in keeping the pace with the quality of the qubits and the number of qubits. And what we know is the more qubits you have, the harder it's going to be to have good fidelity. So that's a challenge. So I will close with the energy question. The energy question is, well, initially, when I started with my co-founders, the Quantum Energy Initiative, our main belief, particularly on these systems, was that maybe quantum computers would bring some energetic advantage. That was a belief, and we switched gear on that for 2 reasons. The first reason is, so far, there are very few situations where with a NISQ system, so a noisy existing system, we are really able to do something that you can't do classically in a cheaper way. So in most cases, we can do it classically, and there have been a lot of progress in tensor network computing, in classical computing using GPUs, which kind of puts a lot of questions on the potential computing advantage and energetic advantage of NISQ. So then we switch to FTQC. And when you look at FTQC, you see the number just later on. The numbers are staggering. I mean, some systems may have significant energy consumption. And so the problem turns into what's going to be the energy consumption of those systems, which are going to be larger than NISQ systems, and will it be acceptable, and can it be optimized? And will there be a difference between the vendors? And so just to look at some pictures, if you look at these pictures, PsiQuantum is installing 3 systems in Chicago, 3 to 4, and 1 in Brisbane in Australia. those systems will consume each one 100 megawatts. IBM is planning to deploy in 2033 the so-called Blue Jay system with 2,000 logical qubits, 6 megawatts. Continuum right now has a NISQ system supporting only 98 physical qubits. The consumption is very modest. It's only 37 kilowatts. It's just the equivalent of one rack of NVIDIA DGX, so it's not a lot. And on the right, you have a couple of vendors, and I miss a lot of them, cold atoms and trapped ions. And here you have silicon qubit companies like Dirac in Australia or Cobley in France. They plan to consume less than half a megawatt for supporting a similar workload than IBM and PsiQuantum. But we don't know if it's going to work. That's their plan. And if you look at those numbers, it looks like the size of the systems, which is huge in the case of PsiQuantum, and the power consumption may become at some point, and I think David is going to talk about this, a key procurement selection criteria on top of the physical qubit, logical qubit, FTQC, and supported applications. And here, there's another thinking. I put the numbers we saw just before, and I put them in a chart where in gray, you have the largest HPCs in the world, and they're ranking in the top 500. And what you see here is, let's take the case of IBM. If you take the case of IBM with its two systems, which are going to be released in 3 and 7 years, so Starling and Blue Jay, there are in between the 72nd system for the small one, Starling, and the 12th largest HPC in the world for the large one. So it means that if you look at the distribution in blue of the potential power consumption of future systems, the power consumption may be kind of in line with the distribution of power consumption of existing HPC based on their power in petaflops or exaflops. So of course, those systems in the chart, they don't have the same power. It's not the same number of logical qubits, not the same number of supported operations, but it gives an idea of the distribution. So the thinking is the following with that chart. The thinking is if FTQC systems have a similar power distribution than existing HPC, it may mean that the market size is going to be in line with the market size of HPC, at least for scientific computing. So it's very important as an observation, even if it's empirical. And so what it means is the market can be very small if the only functional systems are the large ones, like the PsiQuantum or the IBM ones. And the market could be much larger if we have, and we'll have in the future, a lot of systems supporting the same workload with less than 1 megawatt. But because in that case, the market will be in hundreds instead of dozens. So that's very important to consider the market size just for scientific computing in that case. So how you manage this question? To manage this question, you have to understand where is the energy and power being consumed in a system. So the energy is consumed in mostly 3 different places. One is what's in yellow and orange in the middle of my chart. It's all the classical control of your qubits. Mostly it's electronics and photonics. Some of these electronics work at low temperature. It's the dark orange. And some are operating at room temperature. The second is the cryogenics and the cooling. You need cooling whatever you do. You need even to cool a room temperature laser with a water air cooling. But sometimes you need a dilution cryostat to have a lower temperature than 1 Kelvin. And in most of the case, for all qubits, you will need 4K cooling with helium-4. And then in most cases, you need some vacuum pump, but it doesn't cost a lot. And on top of that, you need classical computing before you run your circuit, during the circuit execution, particularly for error correction, and after the circuit for post-processing. So to have a systemic approach, you need to understand where is the energy being consumed. And there are sometimes counterintuitive situations. One is, for example, that the energy that lands on the superconducting qubit is very small. The energy is 10 minus 20 joules. So it's very low energy compared to the cost of generating that energy at room temp, which is about 14 orders of magnitude larger. And it's not just about because of cryogenics, because you need to create some microwave pulse, and then you need to reduce the power that is entering the cryostat, and then you need to reduce the energy that lands on the qubit, and there's a lot of filtering and attenuation all along the path. So there's a lot of inefficiencies in that sense. That's the same for cold atoms, trapped ions. You have a lot of inefficiencies, which is just per qubit for controlling 1 qubit. And I said that quantum computing needs classical computing. It's always hybrid. So in this circuit, I take a quantum phase estimate, which is a very famous quantum chemical simulation solution. You need to generate the circuit. Then you need to compile the circuit into something that's run by the system. And particularly with FTQC, it's very complicated. Then you need to implement error correction and a process called real-time error detection, which needs a lot of power, sometimes up to dozens of NVIDIA DGX for a large system. A batch manager, of course, to manage your system. And then you obtain classical bits and you do some circuit short post-processing. So the green part is the classical part, and the blue one is the very important one, which is very costly. So I'm going to go faster because I think I'm a bit late vs the timing. So what is the QEI about? The QEI was created 4 years ago, and the idea was to create an academic community that was looking at this question. So creating a new field of science and engineering, create methodologies and standards to evaluate, optimize, and benchmarking all these questions and the energetic of all quantum tech, not just computing, but also communication, for example. And in a way, change the rule of the game, making sure that energy is a key procurement criteria. And so we have a scientific board. We organize a workshop every year. The last one was in Barcelona. The next one is in Lisbon, in Europe. And we are also creating a standard. And these are the people in the last 2 workshops. And so our pillars are threefold. One is working on the science, fundamental science. The second is working on engineering. There's a lot of engineering in looking at energy consumption, but also at economics, regulations, policymaker, creating a standard. And if you look at the history of this initiative, initially there was a paper created by my colleague Alexia Ofev, so 4 years ago, which called for the creation of that, and so we created it. There was also another paper from Marco Felus and others providing a first methodology to look at the way you compute and you estimate the energy consumption of a QPU. And the field is emergent. This is very nascent. I mean, we have 1,000 papers every year, at least for the 2025. It's less than 1% of the total papers on arXiv on quantum physics. It's growing more or less in parallel with the growth of papers in quantum physics. I'm working on a specific paper, which I sent, by the way, to David on the energetic challenges of FTQC based on the presentation. And we're working on standardization at IEEE. And there are many counterintuitive facts there, and we may discuss that during our discussion. Cryogenics is perceived as a big problem. Actually, it's not that big a problem, because if you look at the resource estimates for future systems like the IBM one, cryogenics is going to account for only 20% to 25% of the total energy cost. Because the cost is going to come from electronics and photonics. And also, error correction is going to drive a huge cost. In the case of the chip systems, like silicon qubit, error correction, the classical part of error correction, is going to cost 2/3 of the total cost of the system. Another thing is it about science or engineering? It's both, Chief. There's room for progress in fundamental laws, but also room for progress in enabling tech and in engineering. And there's a lot of interdependencies between all the stacks in the thinking around energy. Classical computing, we mentioned that. And the last one is economics. In classical computing, and it's probably going to be the case in quantum computing, energy can represent about 1/3 of the total lifetime cost of the system, so total TCO. So it's going to be significant. And it could double the energetic bill of HPC centers, like the ones from the DOE. So it's significant for the users. We will add a QPU to an existing HPC. I'm going to skip that because I'm kind of late, and just give you some key takeaways after this half-an-hour presentation. So energetics is a nascent field. It's very new. David is going to say the same. The FTQC power consumption may become significant, and it depends on many, many parameters, the quality of the qubits, the technology, the way it's being addressed by the vendors. There's a lot of work needed, and joint academic and industry and users also, including HPC centers. Standardization is needed because we need to agree at the industry level the way you measure the energy and power consumption, because if we can't compare, we can't value anything. And it's going to be the part of the talk from David. Energy is one of the steps towards looking at the whole environmental cost, because you need to look at materials, you need to look at water, you need to look at the life cycle analysis, which is done by nobody right now in the industry. with that, I thank you for your attention, ready for questions, and you can get the slides with your phone and you get it right away. Thanks.
Thanks, Olivier. So in the interest of time, I'm going to encourage the audience here to put your questions onto the chat so that we can move to our next talk, and then we'll have some time for discussion. So I guess I'll welcome David McCollum. So and give a brief introduction to David. Dr. David McCollum is a distinguished scientist at Oak Ridge National Laboratory and a joint faculty professor at the University of Tennessee's Baker School of Public Policy. He has a wide range of expertise that spans economics, engineering, policy analysis, and corporate advisory services. Among the broad suite of methodologies that David uses in his research includes energy economic systems and multi-sector dynamics models, and he, David is well known to a lot of folks in the MSD community for his collaborations and also his leadership in the research to operations to research working group as part of the MSD community practice. So welcome, David, to this webinar, and looking forward to your insights on the resource implications of quantum computing.
Yeah, thanks a lot, Gokul. Appreciate the intro. Yeah, and on that last bit you mentioned, I mean, you and I are co-leading that working group on research to operations and planning. So which is always fun working with you. Do you see my slides in presentation mode? Okay, good. Then let me get going. Yeah, and as we discussed, Gokul had the good idea. We recognize that, so we've scheduled this whole webinar for an hour and a half, but some folks will probably start dropping off at the hour mark. So I'm going to, and I won't be done yet with my talk. So I'll take a breath, maybe at just a couple minutes till, 5 minutes till. We'll see where I am and what I can remember to do. But if anybody has any burning, like clarifying questions, right, then we can take them and then I'll continue. So I'll probably get through the methods and some things, but it won't be yet with key insights and results. Okay, just keep that in mind. But this is being recorded, as has been said in the chat. Okay, let me get my. All right, here I go. Yes, so yeah, thanks a lot for the invite, and it's really a pleasure to team up with Olivier again. We got to know each other more recently. He's truly a pioneer in this space over the last few years, and you could see from his talk how much he knows about this topic. And the work that I and my team have been doing at Oak Ridge National Lab is more recent. Yeah, about a year and a half ago we started, thanks to some internal funding that we have or that we got here at the lab. And it's we just bought a bit off a small chunk of the apple of the kinds of things that Olivier was talking about. But so today I'm just going to describe this one study that we did, that we worked on starting a year and a half ago. You can see by the byline that I say kind of in a cheeky way, it's a topic worthy of deep interdisciplinary study. And that echoes what Olivier was saying. I truly believe this, that we're at a kind of a point in the trajectory of quantum computing that we need a lot of people kind of coming in and studying this from different angles. Because it's still in its infancy by comparison, and it's been awesome, yeah, for me and my team to be working on this. A really fascinating topic. And so who is that team? Yeah, I need to give credit where it's due. I think a couple of them might be here today. So the folks on the top, these are all from ORNL, or at least they were. A couple of them have moved on to professor positions and industry positions elsewhere. But myself, Nashida, Samindra, Melrose, we all come from broadly speaking, the multi-sector dynamic space, doing energy, environmental resource analysis type work. Whereas the folks on the bottom, Sarah, Andrea, Wei Jun, come from the quantum space, either quantum theory, math, the physics, the cryogenic engineering in Wei Jun's case. And it was absolutely instrumental to have those three on our team to make sure that the kinds of numbers that we produced, the assumptions we brought in passed the sniff test, and I think what we ended up producing we're quite happy with. And so what was that? Just in case so I don't forget to mention at the end, and you can scribble some notes down or take a screenshot if you like. These are the main outputs: the two papers in the top right that you see listed there, and then a dashboard there that's mentioned on the bottom that basically summarizes our results. And then there's, if you forget that, just Google some of these keywords and you'll come up with this web page that's on the left, this ORNL web page, which has links to these papers and dashboards. And yeah, hopefully this is just one step on the way to going deeper in this space. So let me take a breath there in case you want to grab anything. And then I'm going to go, okay, yeah, launch into more of the substance of the talk. Okay, so as motivation, big picture. So in case you couldn't tell by Olivier's talk, or if you haven't seen it just elsewhere, there's an enormous amount of excitement around quantum information, science, and technology writ large, yeah, over the past 5 to 10 years. So it's not only quantum computing, but sensing, networking, these different applications that show potentially a lot of promise. The science of quantum mechanics, has been around for just over 100 years. So that goes back to Heisenberg and Schrodinger and these guys. Last year, the UN christened the year 2025 as the International Year of Quantum Science and Technology. And I don't know if any of you get like weekly copies of Science or Nature in hard copy or online, you see that, yeah, basically every single week there's 1, 2, 3, 4 papers around something quantum. It's astonishing, yeah. And there's just advancements being made all the time. There's this one quote that I like that's mentioned here at the bottom from somebody from one of these investment services firms from the Bay Area, venture capital firms, who says, "Quantum could unlock endless possibilities for humankind, akin to asking a genie for infinite wishes." So I don't know if that's true or not. I mean, but this is kind of the thinking that's out there. There's this incredible hope. In some cases, people would say hype, but still, there's a lot of well-founded hope for what could be done. And Olivier already hinted and highlighted a few of those potential applications. Now, a lot of these papers that I mentioned that have been in Science and Nature over the just past years, and a lot of the discussion around quantum, yeah, it's very much in the fundamental science and engineering space. You are starting to see, just in the last couple of years or so, kind of some nods in these papers to the energy and resource side of things. Like they'll say, at large scale, this could, such and such could be a challenge, right? But there aren't, calculations they've done outside of the work that Olivier and his team have been doing and have highlighted. But having said that, because some of this work is kind of getting out there, and it's now kind of these ideas around the public domain, so much so that you're starting to see, like in mass media, BBC, Physics Today, Olivier highlighted that one on the left where he was interviewed, this increasing acknowledgement of the potential future energy and resource impacts. And it's not just about energy, it is about some of these critical materials. Helium-3, this rare isotope, is one of those. And so this is interesting. So these ideas are getting out there, but still not enough deep, rigorous, systematic analysis. But this is what, yeah, as Olivier said, we're trying to build a community around that. Quantum, yeah, is not the only game in town here in terms of these kind of next generation or next generation so-called beyond CMOS computing architectures. CMOS being the semiconductors that we know today, all the CPUs and GPUs. So the other kinds of things that people are studying and show a lot of promise for easily 100,000x reductions in energy or resource use. Neuromorphic computing, so that's brain inspired. People talk about analog computing. There's this DNA computing, which is more for storage, which is biologically inspired. And then there's quantum computing. And so this figure I'm showing here is basically, for lack of a better word, kind of from an expert elicitation of people in the computer scientists community.
We don't see your slides. I'm the only one. I see your face, but not your slide.
I see David's slides.
Oh, you say? Oh, you see?
You.
Oh,
You
sorry.
do? Okay.
Sorry for disturbing.
And I'm not seeing anything in the chat, so because I'm just seeing my slide. Everything okay? Cool.
Okay. Sorry.
Yeah, we can see.
Yeah, we can see him.
Okay. Sorry, guys.
No worries. No, it's good you flagged it. Yeah.
Oh,
Yeah,
because there are 2 windows in my screen. Okay.
Yeah, do holler if something comes up. Yeah, because I'm not seeing you right now. So quantum, you can see kind of from this, quasi-expert elicitation, came from a workshop, is at least the fault-tolerant quantum computing of the type that Olivier was referencing. Yeah, is seen to be kind of, more in this 10 to 20 year time frame. Some of these other architectures a bit further, but they're all quite advanced, and people are working on them in real time, making great advancements. And so sometimes people, well, they have asked me, okay, if this is so, futuristic, why even look at this quantum computing already now? And I mean, one, it's a fun thing to do, to kind of think, kind of beyond where many people's heads are at right now, because this has, really transformational potential. And if you do scenario analysis work, this is definitely in the time span of these scenarios we're talking about, out to mid-century or beyond. But two, so it's a little thought experiment. And if you think about to GPUs, right, which are in all the hyperscale data centers, today, which are sending NVIDIA stock prices, through the roof. The first GPUs were piloted in scientific high performance computing centers, HPC centers, like at Oak Ridge National Lab, circa 2007, right? And then about 10 years later, 2017, you start to see this emergence of these commercial scale AI data centers with millions of GPUs. And then a few years later, early 2020s, you start seeing, just more proliferation, strains on the grid, land, water. And then here we are today, 19 years after 2007, right? So almost, that 20-year mark, where you can see how that that technology trajectory went, right? And so if you then think, okay, could quantum follow that same path? It's not to predict that it will, right? But just again, it's a thought experiment. The first instances of quantum HPC integration are happening in scientific HPC centers, right? Like today. Here's a screenshot at Oak Ridge National Lab just a few weeks ago, where the IQM folks were over here, and they have this little 20 qubit physical qubit system that you see the ribbon cutting ceremony for. Yeah, and this is going to be studied over the next years. Similar is happening in Japan, Europe, Australia. So again, what's 10 to 20 years from now? It's circa 2040 plus or minus, right? And the question is, might we see quantum in these commercial scale so-called quantum accelerated data centers of tomorrow or the day after tomorrow? I mentioned this just, again, it's a thought experiment. It's a bit speculative, but this is kind of the mindset we're in with this analysis that I'm going to show you, right? And I think some people might not realize that there already actually are a lot of quantum R&D centers or hubs, as they're being called, throughout the world. Here's a picture or a map for the US, where there's about 50 or so of them. These are federal quantum R&D centers that's represented by these red psi symbols. And I overlaid that with, the yellow is these, all the commercial data centers that we have today from the S&P data that a lot of people are using. And it's not to say that, any future quantum accelerated data centers would be located in these places, but there is a lot of thinking around that these places, Northeast, Boston, New York, here where I am in Oak Ridge, Tennessee, Bay Area, California, Denver, Chicago, these could be the places where the so-called quantum ecosystem starts to develop in terms of supply chains, and all the componentry, all the firms that produce those components that feed into these systems, because it's a lot and it's really high precision stuff. And then you could draw a similar map for Europe and Japan and elsewhere. Okay, I'm just checking the time. Yeah, let me make through a few slides here on the methods, and then I'll take a breath and get any clarifying questions just before the top of the hour. Okay, so what we did in our analysis is to draw the system boundaries pretty tight, and as I said, not bite off more than we could chew, because there's a lot of these different qubit implementation platforms that are being developed. Olivier mentioned that, trapped ion, superconducting, photonic, We said, let's stick with superconducting. Why? Because those are at least for computing applications, this is the qubit platform that is the most technologically mature. It's the one for which there's the most publicly available data, to the extent there is that much, but there is some, thanks to folks at IBM and Google and Alice and Bob and elsewhere that have published some of their numbers, or at least published their roadmaps for where they want to get to. So we mined that information and brought it into our analyses. So we focus on superconducting qubits. I guess Olivier showed a couple of pictures, but I realized that not everybody will have an image in their head of what these systems look like. So here's IBM's superconducting qubit systems at their facility in New York. I think Olivier's been there in person.
Yep.
Yeah. But these, I haven't, but you can find these online. In a way, it just looks like, server closets for data centers, right? And then you could kind of stack these in parallel just on the floor and just build up larger and larger systems. That's IBM's idea of these modular, their so-called System 2 design. But if you look under the hood, or if you would open up those closets, you're not going to find server racks and microchips and all those wires. You're going to find something like this, right? And this is the dilution refrigerator that Olivier mentioned, this chandelier-looking type structure. That's kind of the heartbeat of it all. At least this is the way to get down to millikelvin level temperatures right now, 0.01, 0.02 Kelvin, just a smidge above absolute zero. So that's colder than outer space. And that's where you basically feed in I can show it in a picture in a couple minutes, but you're feeding in some nitrogen, liquid nitrogen, liquid helium, this rare isotope helium-3, some amount of electricity and water for cooling, and at the very, and it's just progressively kind of moving down the temperature to, yeah, just above it, absolute zero. And at the very bottom tip of one of those dilution refrigerators is a quantum chip, right? And then you can string these together and make these chip modules, these so-called QPUs, quantum processing units. And yeah, and then you've got control electronics, as you can see on the side, that reduce things into the classical space, and then you're off and running with the calculations. So if you kind of zoom out a bit, out of the closet and kind of above the facility, thinking what we all have in mind for what data centers look like today. Here's an image that I find useful, and Olivier showed something similar to this. This comes from PsiQuantum. They do photonic qubits, but it's the same idea, where their conceptualization on the left is that you'd have a compute building, right, with all your quantum equipment and some amount of classical equipment as well. And then outside of that, on the side, you'd have a cryo plant, right? It's producing the liquid nitrogen, the liquid helium, circulating that through the facility, keeping things cold. And then on the right, this is an artist rendering that they've put out. PsiQuantum has for this Illinois quantum and a microelectronics park that's being built on the south side of Chicago, in this former, I forget, it was a huge industrial facility, maybe a steel plant. There's a lot of, it hasn't been used for some years. A lot of public and private funding is going into redeveloping that space. PsiQuantum is going to be the anchor tenant. But I show this because it effectively looks like a data center campus. These big warehouse type buildings, they're connected with, with information, electricity, data, other things just flowing, but back and forth between them. So and I'll take a break just in a second. Yeah, what we needed to do in our case, all this is important for our analysis, because we're trying to conceptualize here for the kind of, let's say, somewhat simple techno-economic quasi-life cycle analysis we were doing. We need to know the flows of things, the inputs and outputs of things, where it's going, where it's coming from, the efficiencies of conversion, and so on. So we need to draw this out for ourselves of what it could look like. And this is what we came up with. It's not a prediction of how it will be in the future, but what it could look like. This is from the help of one of our graphic designers at ORNL, where you've got something, yeah, again, it looks like a data center campus. I know that it may be a bit small on your screen, but you have a building or a series of buildings, but in one of those buildings, you've got some GPUs and CPUs for the classical bits. And another part of the building, you've got the dilution refrigerators where the QPUs are. Maybe these things are more mixed together. We put it here as partition, but the point is that you've got some of this helium-3 that's circulating around inside where the dilution refrigerators are. You've got some liquid nitrogen, liquid helium flowing through the campus, water, high power, a large amount of power coming in from the transmission lines. And then from that, we then kind of built out let's say, an accounting tool that looked at the energy and resources and the flows of those. So, and we refer to this, Nashida on the team, who's I think here, came up with this this term, quantum accelerated computing infrastructure, or quasi for short, and I'll use that a bit more later. So let me take a quick break there. I'm going to get into some numbers and then some results after that for another 10 minutes or so. Any burning questions? Go cool. Tell me if you see anything.
So I see one question on the chat, but that's for Olivier. So maybe we can take that. I think that's like more of a discussion kind of a question. And Olivier, just a nudge for you to maybe monitor the chat a little bit if you want to maybe start responding to that question on chat. But I think we can take the couple minutes to see if anyone has burning clarifying questions for David or Olivier before they need to leave. If not, we'll have David continue and we'll take up questions during the discussion.
Okay. Should I keep going?
Yep, hearing none. So let's keep going.
Yeah, unless anybody wants to jump in, it's all good. But yeah, we wanted to, by design, we wanted to make sure we left a good chunk of time towards the end for proper discussion. So we can, if anything comes up then, all good. Okay, then let me keep going and I'll try to keep moving quickly. All right, so this next slide, warning, bit information overload, but that's by design. I'll walk you through it. You don't need to look at every number here, but I'll guide you through the key numbers, and you can find all this in our paper as well in the supplementary material. But what we needed to do in this case, again, not knowing, as Olivier has said very well, how these quantum systems of the superconducting type only, how they're going to look in the future, how they're going to be spec'd out, right? there's a lot of technological development that needs to happen beyond today to get to these, to these more commercial scale systems, right? That could be used for transportation and electric utilities, finance, and so on. So we said, all right, let's develop 3 different configurations, in a way, scenarios of technological optimism, you could say. And it's what we see here in these 3 columns: yellow, pink, and blue. It's almost like a small, medium, large in a way, or you could maybe think of it as optimistic, very optimistic, very, very optimistic. But these, so in quantum speak, this one in the yellow is a so-called practical fault-tolerant quantum computer. Then the ones in pink and blue, full fault-tolerant quantum computers, both a smaller and a larger. These ones in pink and blue, the full fault-tolerant quantum computers, they would be large enough and they would have these error rates low enough that they'd be capable of doing all the things that people are very, very excited about with quantum, breaking the RSA 2048 key. A lot of people are scared about that, but solving complex chemical simulations, optimizing industry scale algorithms, and so on. That one that's in yellow, the practical FTQC, wouldn't be that powerful. It wouldn't have the error rates that would be needed, but it'd still be a pretty powerful machine that could be used for a lot of things. So all these systems are way beyond today what we have in terms of qubit counts. But what you see here, just looking at the table, I'm just showing this to kind of give you a sense of how we had to build this up kind of from the ground up in a way. The kinds of things, if you were analyzing, doing, I don't know, a power plant or a car or something, you just kind of build things up, in terms of its the engine, the transmission, and so on and so on. And you need to know the number of logical qubits. That's where a lot of the calculations are done. You need to know this ratio of the physical to logical. That determines the error rates that we're talking about. That's the 3rd line here. That gives you a total number of or a base level for the number of physical qubits. Then you need even more physical qubits to do because of the error correction that Olivier discussed. So that gives you a number, and that's kind of in this, I don't know, a line midways down. Total physical qubits needed, and it's about, are these 3 systems, 200,000, 4 million, 20 million. Again, these are enormous systems compared to what we have today. Remember that one at ORNL that I mentioned had 20 physical qubits, right? And some of the other ones are in the hundreds or even 1,000 qubits today. So this is way bigger, right? But again, we're talking 15-ish years from now, right after a lot of development. The reason this is important is because we have these different numbers of qubits, and then we had to make assumptions for essentially the density. How many of these qubits can you fit in a confined 2- and 3-dimensional space, right? And then that determines how many dilution refrigerators you need, how many cryostats you need, how much floor area do you need, how much and then eventually the flows of electricity, water, and the cryogenic gases. Okay, so we went through all that, and we calculated, and I'll just say this quickly for electric power demand. So wall power, we kind of bucketed these into different categories: the control electronics, the cryogenics equipment, the cooling water infrastructure, because you're going to need chillers, cooling towers, there's all these pumps and compressors that are bleeding out heat, and you need that, some base load and miscellaneous demands, just for things like ventilation, cooling, and so on that you'd have at any data center, right? So add all these things up, a lot of assumptions in the process, but we would do a big sensitivity analysis. And then on the water side, as mentioned, there's a lot of compressors, pumps, liquefaction devices, these pulse tube mechanical cryocoolers that are moving around. Everything's bleeding off heat, so you need a lot of water flowing through to cool these things down. And so that's, we added that up as well. And what you get to, and this starts to move, it's a bit assumptions, but it's also moving into the results as well. What you get to, and this is, look at this top line here first. This is electric power for a single FTQC, so not multiple ones linked together, but just a single one. Here on the top line is represented by watts per qubit, physical qubit, for these 3 different configurations that I mentioned, the small, medium, and large. And this watts per qubit, I know these numbers don't mean a lot to folks who haven't looked at this literature before, but it's becoming a common metric in let's say the energy and resource analysis community around quantum. It's kind of like a miles per gallon number for a car, or maybe better, like in European terms, like liters per 100 kilometers, because the lower the number, the more energy and resource efficient it is. And so you're seeing values here in the 60, around 7.2 range, compared to, this is in the future, again, compared to values today that are in the hundreds or above 1,000, right, watts per qubit. So there's a lot of progress that's being made. I think folks will have a better sense of the lower row in terms of megawatts, and this ties back to Olivier's numbers as well. These future systems, that at least that we spec'd out, on the order of 12, 27, 4 megawatts, again, for a single FTQC, which is, right in the range of today's HPCs that we have. I think the 27 number is almost right exactly around what we have at ORNL, the Frontier machine, which is the third fastest HPC in the world. Now, also another comparison point, if you look in some of these in the right column in gray, the biggest cryogenics facilities are in the world, like in France at the ITER nuclear fusion facility or the CERN at the Large Hadron Collider, they're running at 26 to 40 megawatts, depending on the day and the time of year and what processes they're running. So we're right in that range, right? So I think that's good for a comparison point. In terms of water, again, same structure of the table, and I think similar insights as well, but just on a different topic. In terms of direct consumption of water, so forgetting upstream power plant electricity production and the water that's needed for that. So forgetting that, just the direct consumption, we're talking in the order of 40, 30, 40, up to 100 million liters per year of direct water consumption. Which compare that to today's data centers, which are in the hundreds or thousands of million liters per year. So I mean, in that sense, the single quantum machine is quite small. But there is this question that nobody knows the answer to right now. We won't know for a while. Is how many quantum machines of the types we're talking about are going to be situated at a single data center of the future, right? We don't know that. And if you have a few of them together, well, then you're already quickly up into the hundreds million liters per year, which is not so different from the data centers that we have today. I think an easier way to look at it is and some people maybe have a better feeling for these numbers, is the bottom row, which is water use effectiveness, WE, which you see Google, Amazon, others reporting all the time now. It's basically just liters of water, direct consumption per kilowatt hour. Here we calculated 0.4, 0.8. It's pretty much exactly around what we're seeing from Google, Amazon, and others at their data centers in the world, which is, you can see a note in the bottom right of the table, 0.7 to 1.5 liters per kilowatt hour. So let's see. Key findings and insights, and I'll start to bring this to a close here in the next few minutes, because I think we wanted to, again, to keep zooming up, to build from the level inside the facility, and then above to a single potential facility, and then all the way up to kind of the national level. What does this mean at the end of the day to put these numbers into into a scale that many people have a feeling for, right? And so we did a very simple, admittedly simple scenario analysis where we looked at the S&P data for data centers. We have a recent version of that, and in that data set, it has basically projections for data centers out to 2030. It's the ones that are planned and on the books for the next few years. We looked at cloud, crypto mining, hyperscale. It's basically by 2030, I forget exactly the numbers, but around 75 new data centers per year are coming online just in the US, right? So we did this scenario analysis just for the US. We said, let's extrapolate that into the future, right? Every year from now through 2050, so 2045, so 20 years, 75 new data centers are coming online. In the US, that's 1,500 total. And then we said, all right, now somewhere along that timeline, probably not the next few years, but closer to 2040 or so, some amount of those data centers are getting quantum computers added to them, right? Either all of them by 2045, or maybe just 10% of them, right? We wanted just to span a big range. And then we said that every single one of those facilities, if it would happen, would, this is a big if, right? There would have 2 of these FTQCs, right? Just for redundancy purposes. You wouldn't want just one. But so we said, let's have 2. I mean, it could be more. It could be 4, 8, more. I don't know. So that gives us 6 of these scenarios total, right? These 2 penetration cases, the 10 and 100%, and then these 3 tech mixes that I mentioned before, the practical and the full FTQC, the small, medium, large that I mentioned. So with these scenarios, we did all the calculations, did all the accounting for that, calculated electric power, the water I mentioned, nitrogen, liquid helium, the isotope helium-3, and then that's what you see in all these bars and all these different figures, 6 bars per figure. I'm not going to go into this right now, but this is what you see in the paper. Here, just the key insights, right? I'll just hit you with the highlights and the need to know information. on the electric power side, what we found is that if you had a fleet of these so-called quasi facilities, across the U.S. by 2045, again, according to the different scenarios that we spec'd out, the electricity demands are within reason, I would say, in the single digits to, in the tens of gigawatts. Compare that to today, the total US grid has a capacity of 1,000 gigawatts. It's running on average at about 500 gigawatts. This is, of course, growing as we know, but that's more or less where it is today. So, single digits, tens of gigawatts. Yeah, it's relatively small. But again, the question is, how many of these FTQCs are we going to have in a single quasi facility of the future? If it's 4, 8, 16, then clearly these numbers then balloon pretty quickly up into the hundreds of gigawatts. And who knows if that's going to happen? That would be a pretty big constraint in the end. And Olivier was getting to that as well with his talk. But just to give a sense of the numbers, and then similar for cooling water, I'd say the direct consumption, similar order of magnitude as today's AI data centers, especially if you have multiple FTQCs per facility, which means in water-rich regions, that may not necessarily be a challenge, but in water-scarce regions, it very well could be. We also have to remember that, even for today's data centers, the thermal management technologies are evolving pretty quickly. There's these things, some of you have heard of them, direct-to-chip, immersion, two-phase spray. Some amount of those technologies probably could be applied into quantum systems as well, but not all. But that's an open research question, I would say. I'm not sure who's looking at that, but it's an interesting one. So that's one caveat with the water numbers. I think more interesting, to me at least, and to my team, that we were looking at the cryogenic gases, because there haven't been many studies that I'm aware of that have looked kind of at large scale, future cryogenic gases, helium, nitrogen, and what the demands are and the supply chains and so on. So we found first for helium-4, that's the common stable isotope of helium, what you put in party balloons and so on. This is, well, actually, I don't know how many people know that. It's not a renewable resource, so it can't be manufactured artificially. It's coming from typically in the US, natural gas extraction, and they pull it from that, but there's less of it in fracked natural gas, which is now a large part of US natural gas. And so there's just not as much of the helium that's just right there available. And so the US and global supplies are tight, demands have been rising, prices have been rising. A lot of the big users of helium-4 in recent years are recycling and reliquefying and just not releasing it to the atmosphere. So in that sense, if that would be done for quantum facilities, and I guess it would be, then this isn't going to be a deal breaker per se for quantum computing centers. But then there's the helium-3 as well, which is an isotope of helium, has one less neutron. And this, as I mentioned, is this crucial ingredient for getting down to millikelvin level temperatures, and really the only practical way to do it right now, although there's some other methods that are being explored by scientific institutions throughout the world. But point is that helium-3 extremely limited on Earth, right? It comes from tritium, which comes from spent nuclear fuel or decommissioned nuclear weapons. In the US, at least, those then go to the Savannah. The tritium goes to the Savannah River site in South Carolina. They pull helium-3 from that. And then an industrial gas supplier takes it to universities and labs and airports and whoever else needs the helium-3 for different applications. It's not there are no public figures, or we don't know with certainty how much helium-3 there is for security reasons. On the order of tens of thousands of liters per year are produced between the US, now Canada, also Russia. So we did a calculation. If you would just say, let's forget all the uses of helium-3 today, all those things that I mentioned, just apply it all to quantum computing, then maybe you could supply, as you see here on the bottom bullet, maybe 5 to 20 FTQCs per year worldwide. So 2, 3, 4 data centers that have quantum. So not many, right? And this is one of the key reasons why that there are some startup companies that have come into the mix in recent years who are trying to find helium-3 on Earth. There's some pockets they think might have more, like in northern Minnesota. There's a drilling activity. I show the picture here, this Topaz site. And then also there are companies that are planning to go to the moon to mine it, because there's just higher concentrations of helium-3 in the regolith, the soil of the moon. So that's an interesting thing. And I think with that, I had a couple more slides, but I wanted to, let me skip this about noise, which was just to say, actually, noise could be just as much or more of an issue than for today's data centers. And final thoughts. Okay, this is basically the last slide. Yeah, there's a lot to be, as has been mentioned by Olivier, there's a lot of work to be done on the technology side of quantum, these different qubit platforms, a lot of things that will be discovered that we just don't know yet, a lot of surprises, I'm sure, in a good way. So a lot of uncertainty in this space of how far we can squeeze down the energy and resource efficiencies of these systems. But from my and my team's perspective, I think some uncertainties that are just equally or if not more important are kind of on the social side of things, socio-technical side of things. Namely, this question is, what services will quantum provide in the future? Will it be restricted to advancing, novel drug discovery, material science, traffic routing, the things that people are talking about, or more in this business operations side of things that Olivier highlighted, so it's basically satisfying new demands for consumers and businesses around crypto mining, social media, online shopping, We know that quantum is not best placed for AI inference kind of stuff, like ChatGPT. It's probably more for, optimization, training models, and other things. But there's a lot that can be done, with that. And I'm sure in 15 years from now, there will be all kinds of creative uses for that. And so it gets to this question, at least the analogy that I have in my mind is these future quantum systems could be something akin to like a Formula One vehicle, this incredibly powerful, highly tuned piece of machinery versus your standard, car that the rest of us drive around town. And are you really going to use that fine-tuned piece of machinery, the F1 vehicle, to do, daily errands and so on? No, it's probably going to be used for the things that are really that generate a lot of profit, basically. And what will those be? We don't know yet. And so this leads to the question is, will quantum serve as a substitute or a complement for classical computing? So if it's a substitute, then we can decrease some of the energy and resource use. But if it's a complement, then it could unleash, unimagined new possibilities for compute, and that would be a different situation. Olivier highlighted this as well. So this is Jevons paradox. This is Jevons paradox in a nutshell, as some of you are aware. So the last final slide was just to say, time to entangle, to use quantum parlance. Time to collaborate, interdisciplinary collaborations. Now's the time for that, both on the fundamental science and engineering side, and those of us who are here on the MSD, the multisector dynamic side of things too, spanning energy and environmental analysis, the behavioral science type work, economics, and more. So with that, I'll close and I'll leave it here on this slide, which has the some of our outputs. Thanks.
Thanks for that, both Olivier and David. It feels like drinking from a fire hose. It's a lot of information, but I think this is a very, very important topic, and I'm glad folks like you all are already thinking about this and sort of like pioneering some research and modeling in this area already. So I guess we have about 12 minutes for Q&A and discussion. So let me first see if people, in the audience have any questions that they'd like to bring up to the floor. If not, maybe I'll probably go ahead and request maybe Olivier to expound on maybe some of the questions and the discussions on the chat already. So maybe we can start there while people are getting or putting their questions and thoughts together.
Yeah, there were two questions. I responded in writing to one of the questions. The other one was about what can we do with climate-related models on FTQ systems. It's a typical chicken and egg question, because on one end, you need the hardware to run a significant quantum circuit to solve complicated problems. On the other hand, you need to make sure that there are quantum algorithms. So there's kind of research in parallel going on. So if you look, for example, at what Google has been doing recently, they've been doing a lot of resource estimates to simulate chemical dynamics. And so they gave numbers which are staggering, number of gates, number of physical qubits, number of logical qubits, and then it gives an idea of what the hardware is needed to solve these problems. That has not really been done in climate-related models, as far as I know. There are a couple, I would say, case studies or use case papers on that, which give some estimates. Sometimes these are toy models that are being deployed only on NISQ systems, so just toy models. It doesn't work better than classical systems. And so what academic researchers need to do is to start with those toy models and then expand those models to a functional one with real-life data, real-life models, and see if it scales well. And one of the key, I would say, challenge for both academics and the industry is data ingestion or data loading. Because when you want to ingest data in a quantum system, you need to find very efficient ways of encoding the data because encoding the data needs gates. You need qubit gates. You need to run a circuit just to get the data before you do anything with it. So it has to be optimized. And so what people say usually in this world is that quantum computing is good for small data and high complexity. So when you have a lot of parameters, a lot of dimensions, like in chemistry, so in chemical simulations, you don't have that much data. Yeah, you have maybe definitions of orbitals in molecules, in atoms. It's not big data. But climate change and climate-related models may be different. There are probably some climate models which are not as huge as the weather forecast models because they are more multi-dimensional, maybe fewer data, but I don't know well about the field, so you need to look at this. The other question in that question was very interesting is how are we going to use those systems, FTQC systems? And it was more or less presented by David. There are going to be two different cases, a bit like HPC right now. The one case is you're going to use a public sector HPC facility, like the EuroHPC in Europe or the DOE sites in the US. In most cases, you use them on a project basis. So you need to apply with a project and you apply for getting some computing time. And based on the utility of what you're asking for, you're going to get the time. In the case of the commercial space, where you want to use you will need to use an FTQC system being hosted by Microsoft or Amazon or Google or whoever, then it's going to be a pay-per-view, like Netflix. You will pay for computing time. Right now, if you want to rent a NISQ system, it's about $2,000 to $3,000 an hour of computing, which is not that much because usually the computing time is very small. But if you use the system for a couple days or weeks, and the computing time is much larger because the size of the system is going to be bigger, then you will have to pay for the computing time you're using. And we don't know yet what's going to be the balance between those two ways of using the system. If quantum computing is mostly a scientific computing domain, it's going to be public sector HPCs. And if it becomes a commercial domain with optimization, financial services, transportation, stuff like that, then it's going to be more commercial market with cloud vendors. And then in between, people who need their own on-premises systems for security reasons beyond the defense and intelligence industry. So let's say banks, for example, the banks, they may need to have their own systems for security reasons, or even anybody doing weapons. I mean, Lockheed Martin, Northrop Grumman, and so on, they will need their own systems probably.
Great, thanks for that, Olivier. So maybe David, if you had any thoughts about one of the questions on the chat, I think there's a question about the likely vulnerability and resilience of quantum systems to acute hazards.
I saw this question. This is a good question, and I don't have like the precise answer, but it's something that we raise in our paper. We raise the same question in our paper, and it deserves future study. The question, I think it's in a section that we called like future siting considerations for quantum systems and resilience. And the thinking is, would those be different than the considerations people have today for the big commercial data centers, which is around land availability, water availability, grid interconnection access, but climate hazards is one of those, right? Would those be any different for quantum? The same ones would still apply. There's one other consideration that you see a little bit in the literature is about because electromagnetic interference, like from cosmic rays, is a potential issue. That's not a extreme weather event hazard per se, or maybe people could look into it. But I think that matters more about altitude than kind of where you are, on the land surface. Anyway, the one point I wanted to make is that, I forgot to make it during the talk, is that I find it interesting. If you think back to the kind of the conceptual the diagrams that we were showing from the companies like Quantum, but also ours. These future data centers for quantum are kind of marrying compute and the petrochemical industry on the same site, right? Like industrial gases and so on. And those, the latter, the petrochemical bits, may be more exposed to certain hazards, extreme event hazards, and not the compute. But you can't do the latter without the former, right? So it creates an interesting dynamic that we haven't seen in the data center world much until now, but are starting to. Like if you think about all the big behind the meter, gas turbines that are being built, right? Chevron and Microsoft just inked a big deal, right, for a huge amount of electrical capacity from gas turbines. That's effectively what's happening, is this marriage of petrochemical, company, oil company in that case, and a data center. So I don't know. It's a long-winded answer just to say it's the right question to be asking, Carl. Yeah, thanks.
I could add a couple things. There are some constraints within the data centers for FTQC systems, which exist already with NIST systems. These are about noise, vibrations, and temperature variability. The constraints are much tighter than classical computing. So for example, if you have cold atoms, you need to be very stable in temperature, no vibration, no noise, because it can damage the qubits. So it explains why in existing data centers, particularly the ones I know well in Europe, in your HPC data centers, usually the small NIST quantum computers, they are in a special location within the data center. They have a special room, which is isolated from the rest of the data center because it must be not noisy, very low decibels. I mean, it's less than 60, 50 decibels. It should be very stable. The variability in temperature is less than half a degree. I think it's even 0.1 degree. So it's very constrained. There's a lot of constraints there. So it means that earthquake would be a problem, probably. So, but it's within the data center, so it's managed by the data center. That's the role of the data center to accommodate for the constraints of the system. So there are specs when you deploy the system.
Great, thanks. There's one question that came up on the chat, and I think it's a question that sort of very similar to one that I had in mind as well. So David, you mentioned in terms of material requirements for quantum computing, helium-3 is like sort of among the most important ones, but there are also potentially other minerals and materials. I think that we had a quick email conversation about that you alluded to. So yeah, if you could talk about the broader material requirements for quantum computing, and in terms of like from an analyst perspective, like a modeler's perspective, we need data to be able to quantify all of this. So and I think Yong's question on chat is pointing to that, which is like, is it fair to assume, or can we leverage existing information and data on classical computing and material requirements for classical computing to make some judgments or informed guesses about quantum computing material requirements while the technology is still being developed? As you mentioned, it's likely going to be more prevalent in the next decade. So to make some informed judgments and informed modeling, can we leverage existing data, and to what extent can we do that?
Well, I can give you a two-part quick answer. I'll try to be brief, and I'll pass it to Olivier as well, because I'm sure he has some thoughts on both. On the second part, Young's question, yeah, I mean, this is a new stuff, and we thought about this in our analysis. What can we leverage from the classical computing type analysis? Work on today's data centers for future quantum. The thing that pops in my mind the first is the water aspects, because we were trying to draw some essentially some reduced form type relationships for cooling water needs for chillers and cooling towers and so on. Maybe we could have done a better job there, but it's a good place to start. But a lot of the other type of equipment is just very different, right? You don't need cryogenics at these other today's data centers. So that's one thing. Second, yeah, it's a long answer, Gokul, about kind of other types of critical materials. It's something that's very ripe for future study. But the kinds of things you hear being mentioned beyond helium-3, niobium, molybdenum, tantalum, and so on, that are used in highly specialized applications maybe either it depends on the qubit type. And sometimes in certain lasers, high power lasers, they need things that the superconducting systems wouldn't need. And I think one thing that we try to do in our analysis, at least just at the very least for the helium-3, was to kind of point and say, look, if scaled up, that's a potential issue. Red alert, red alert. Let's think of ways that, if we see that bottleneck coming, does that suggest that we should be looking at other architectures, or maybe we should try to open up new supply chains for that, and so on? But the same question could be applied to molybdenum, niobium, and so on. I don't know, Olivier, did you have any thoughts on that part?
Yeah, I'd say another one, which is there's a lot of uncertainty on the cost of those machines. Even if I take your slide when you compare the various scenarios around IBM, I mean, there's a huge connection between the cost of those systems and the cost of error correction. And the cost of error correction depends on two things where there's a lot of uncertainty. One is the connectivity between the physical qubits, and the better off you are there, the lower the overhead is with error correction. The second one is how do you improve the physics of the qubits to reduce the noise and to improve the fidelity. So there are a lot of progress that can be done in those two spaces, which explains why in some cases cold atom companies provided very low resource estimates recently for some of their systems. So I would say that it's a positive thing. There's going to be a lot of innovation at the physics level, at the logical level when you, on the way you implement error correction. So there's a lot of papers coming from Google who are improving by 2 orders of magnitude, in some cases, the cost of error correction. And the other one, which is in the paper I'm working on that I sent to you, David, is all the stuff that's happening in cryogenics and electronics. There's a lot of potential improvement in the cost of those systems which control the qubit or cool the systems. So all in all, and if you account for some qubit modalities, like silicon qubits, cold atoms, trapped ions, they may land in a very cheap zone in power consumption, way lower than IBM and PsiQuantum. So if you have systems which cost just a couple hundreds of kilowatt, I would say it's good. It's good for the industry because it's going to be very modest in comparison with large HPCs. And what I don't know is whether Darwin is going to win in the quantum space, because this famous sentence from Darwin is only the fittest survive. So will the fittest survive in the quantum space or not? We don't know yet, because we don't know yet if the physics of the small footprint systems are the ones which are going to work from the scientific standpoint. We don't know yet.
Thanks. So we are a couple minutes over our time, so I think we will we'll probably close the session here. Turn the floor to Pat, and I encourage people. I know there are some questions probably that are left unanswered, but I think I'll encourage them to reach out to the speakers and continue the conversations as needed. Yeah, thanks, David and Olivier, and I'll turn the floor to Pat.
Thanks everyone for your time and attention today, and this was really engaging. Yeah, and a lot of compliments in the comments too, in terms of a really nice, thought-provoking webinar. So thank you all for your time, and we're planning on posting this to YouTube, so you can check out the MSD YouTube channel. So
cool.
Thank you all.
Thank you for hosting us. Bye-bye.
Thanks, everyone.
Everyone.